Hello sailors, I'm Captain Tom Tersey from the Maryland School of Sailing and Seamanship. When sailing, it's often necessary to measure distances either to a fixed object such as a shoreline, a moving object such as a ship, or the distance that we've traveled. As we all know, this modern age of super electronics offers many sophisticated devices to make these measurements very quickly and at the touch of a button. However, these devices sometimes fail, and over-reliance on them can lead to serious navigation problems for the unprepared sailor, and can also steal from our enjoyment of self-reliance. After all, most of us sail to get away from our comfort zones and experience real-world challenges and the many marvels that come with that. Let's take a look at a situation that we all regularly face when sailing. There's a point of land to leeward that we need to clear on our present course. Will we make it, or should we tack? To help answer this question, we can use a navigation procedure based on the changes that occur in the magnetic bearings to that point of land as we approach it. I'll call this method distance off by bow angles. A bow angle is the angle of a bearing to an object taken relative to the bow of your boat while you hold your boat on a steady course. Let's look at an example. You are sailing close haul on starboard tack on a course of 85 degrees per ship's compass, and you see a point of land ahead and to port. Wind is blowing from the southeast, making the point of land into a lee shore. Shallow depths extend out quite far from the point of land, and we would like to clear the 6-foot depth contour shown here by a comfortable margin since the tide is falling and we draw 5.5 feet. To monitor our progress and the probability of safely clearing the point of land, you take a bearing on the point and read 55 degrees across your ship's compass. The time is 0940 and your boat speed is 6 knots. 15 minutes later at 0955, while continuing on the same course and speed, you take a second bearing of 35 degrees on the point of land. And you want to know how close you will come to that point when passing it. This is referred to as the closest point of approach, or CPA. The classic navigation text, American Practical Navigator, written many years ago by Nathaniel Bowditch, gives a method for solving this CPA question in Table 18 titled Distance of an Object by Two Bearings, and the accompanying text in paragraph 821. To use this table, we first need to calculate the angle of our two bearings relative to the bow of our boat, which I'll refer to as bow angles. We're on a boat course of 85 degrees per compass. The first bearing on the point of land was 55 degrees per compass, which, when subtracted from the boat course, gives a bow angle of 30 degrees on the port side. The second bearing on the point of land was 35 degrees, giving a bow angle of 50 degrees to port side when subtracted from the 85-degree course. We also need to calculate the distance that the boat sailed over water between the times of the two bearings as follows. Elapsed time between the bearings equals 0955, the time at the second bearing, minus 0940, the time of the first bearing, and that equals 15 minutes or a quarter of an hour. So the distance traveled between the times of the two bearings is 6 knots, the boat speed, times 0.25 hours, and that equals 1.5 nautical miles. That's the distance sailed over water between the times of the two bearings. Now let's look at Table 18. Across the top are choices for the first bow angle in 2-degree increments between 20 degrees and 32 degrees, and on up to 136 degrees on the subsequent pages not shown. And down the left-hand column are choices for the second bow angle in 2-degree increments between 30 degrees and 160 degrees. Find the first bow angle of 30 degrees on the top row and the second bow angle of 50 degrees in the left-hand column. Where these intersect, we find two factors, 1.46 and 1.12, which are used as multipliers to answer the following questions. Question 1. How far are we from the point of land at 0955 when the second bearing was taken? To answer this question, we multiply the distance traveled over water between the times of the bearings, 1.5 nautical miles, by the first factor, 1.46, from Table 18. So distance to point of land at 0955 equals 1.5 nautical miles by 1.46 equals 2.19 nautical miles. That's the distance to the point of land at the time of the second bearing. Question 2. How far will we be from the point of land at our closest point of approach, CPA? For this, we multiply the distance traveled over water between the times of the bearings, 1.5 nautical miles, by the second factor, 1.12, from Table 18. So distance from CPA to point of land equals 1.5 nautical miles times 1.12 equals 1.68 nautical miles. That's our expected distance from the point of land, CPA, when passing it a beam. Question 3. When will we reach the closest point of approach, CPA? To answer this, we first need to calculate distance from the 0955 position to the CPA, which we can get from the Pythagorean theorem on triangles as follows for a right triangle, where the hypotenuse of the triangle is the distance, 2.19, from the 0955 position to the point of land, and the altitude of the triangle is the distance, 1.68, from the CPA to the point of land. So the distance from 0955 position to CPA equals the square root of hypotenuse squared minus altitude squared. And that equals the square root of 2.19 squared minus 1.68 squared. And that equals 1.4 nautical miles. So the time from the 0955 position to the CPA equals 1.4 nautical miles divided by 6 knots, our boat speed. And that equals 0.233 hours, and that equals 14.0 minutes. So you now have an estimate in advance of how close you'll come to the point of land when passing it to help you decide whether to tack or to continue on course. This process can be simplified by using the boat's distance log instrument to determine distance run between the times of the two bearings, rather than basing this distance on average speed times time interval. Also, use of the distance log is more accurate than basing distance on average speed, since it is difficult for the helmsman to come up with an accurate average speed, since his attention is focused on sailing the boat and other tasks as opposed to just concentrating on speed. In this case, you would read the distance log at the time you observe each bow angle, and to take the difference in these logs to compute distance run in the interval between the two bearings. For example, the distance log read 67.3 nautical miles at the time of the first bearing and 68.8 nautical miles at the second bearing. The distance traveled over water is the distance between these log readings, or 68.8 minus 67.3 equals 1.5 nautical miles between the two bearings. This is a simple subtraction which eliminates the need to multiply speed times time to calculate distance. When sailing short-handed, it may not be possible to perform all the calculations previously shown, so a simplified expedient may suffice to give you an approximation of your expected CPA when passing the point of land as follows. In advance, remember one combination of bow angles, such as 30 degrees and 60 degrees, and the associated multiplier factors from Table 18, which are 1 and 0.87, and use these factors for making a quick mental approximation of CPA without the need for paper and pencil. While this expedient provides a quick approximation of CPA, it does, however, eliminate the flexibility of using any of the many combinations of bow angles given in Table 18 as follows. In the first example in the beginning of this video, we were able to take bearings on the point of land at any time of our choosing, convert these bearings to bow angles, and look up these bow angles in Table 18 to obtain the two multiplier factors. The result of this is that we could shoot the bearings on the point of land at any time with the knowledge that we'd be able to find the resulting bow angles and multiplier factors in Table 18. But when using a predetermined set of bow angles, such as 30 degrees and 60 degrees, these bow angles can only be shot at the instant that they occur as you proceed along your course. At the instant of 30 degrees, and again at 60 degrees, you must read the distance log or the clock time in order to compute distance run between the two bow angles. So let's continue with the example of remembering in advance the bow angle combination of 30 degrees and 60 degrees and the two associated factors from Table 18, which are 1 and 0.87. Notice that 60 degrees is the double of 30 degrees. A doubling of the bow angle such as this sets up an isosceles triangle where two sides are of equal length as shown in this diagram. And that is what the first factor of 1 in Table 18 is telling you. This is a multiplier factor. It is a ratio between distance run and distance off at the time of the second bearing. And a ratio of 1 means that the two sides of the triangle are of equal length, and therefore distance run between the times of the two bearings equals distance off at the time of the second bearing. To help clarify this, let's look closer at the geometry of triangles. In all triangles, regardless of proportions, the three internal angles, when added together, will total 180 degrees. This is just a fact of geometry. The first bow angle of 30 degrees is an internal angle of our isosceles triangle. The second bow angle of 60 degrees is external to the triangle, but it defines the internal angle at the point of the second bearing to be 120 degrees. So, two of the internal angles of the triangle are known to be 30 degrees and 120 degrees. Subtracting these two angles from 180 degrees yields the third internal angle of 30 degrees. Now, since this triangle has two 30-degree internal angles, it therefore has two sides of equal length as shown. As you proceed along your course, you will need to determine when the point of land bears at the bow angles of 30 degrees and 60 degrees. To do this, convert the bow angles to magnetic bearings and use these magnetic bearings to indicate when you reach the 30-degree and 60-degree bow angles. To convert port side bow angles to magnetic bearings, subtract them from the boat compass course. Starboard side bow angles are added to the boat course. This is due to the clockwise sequence of compass numbers. As in this sketch, your boat is on a compass course of 85 degrees, and subtracting the 30-degree portside bow angle gives a target magnetic bearing of 55 degrees to the point of land. I call this a target bearing since you need to do this calculation well in advance to be ready to observe this bearing at the time that it actually occurs. Likewise, subtracting the 60-degree bow angle gives a target magnetic bearing of 25 degrees to the point of land. As in this diagram, maintain the boat on a steady course of 85 degrees per compass and observe the decreasing magnetic bearing to the point of land. Initially, it reads 65 degrees over the compass and decreases to 55 degrees, at which point the bow angle is 30 degrees. Immediately note the distance log reading, 67.3, or the clock time, 0940, needed for calculation of distance run. Continue on course and observe the continuing decrease of the magnetic bearing to the point of land. When it reaches 25 degrees, immediately read the distance log, 69.2, or the clock time, 0959. The distance run over water then, between the times of the two bearings, is the log readings 69.2 minus 67.3 equals 1.9 nautical miles, or 6 knots times 19 minutes divided by 60 minutes per hour equals 1.9 nautical miles. As previously mentioned, the first multiplier factor, 1, from Table 18 indicates that the distance off at the time of the second bearing equals the distance run during the time between the two bearings, which was 1.9 nautical miles. So this eliminates one calculation, and the distance off the point of land at the time of the second bearing is therefore 1.9 nautical miles, same as the distance run. The second factor, 0.87 from Table 18, indicates that the distance off at the closest point of approach, CPA, equals 0.87 times the distance run during the time between the two bearings. This can be simplified for expediency by rounding 0.87 up to 0.9 and calculating distance off at CPA by mentally multiplying 0.9 times the distance run during the time between the two bearings. This expedient approximation, 1.71 nautical miles for CPA, is fairly close to the previously calculated CPA distance of 1.68 nautical miles given in the first example of this video. The discussion up to this point has not accounted for wind leeway and current. But wind leeway and current are significant realities that we need to deal with in actual situations. Even a well-trimmed and well-sailed boat can experience a leeway angle of 5 to 10 degrees or more, and this leeway will push us towards the point of land and reduce our closest point of approach. Also, following current will reduce the log measurement, or speed times time measurement, of our distance traveled and thereby reduce our estimate of the distance to the point of land. This means that with the following current, we will actually be further from the point of land than indicated by the bow angle data and the calculations. Conversely, an opposing current will increase the log measurement, or speed times time measurement, of the distance traveled and thereby increase our estimate of distance to the point of land. This means that with an opposing current, we will actually be closer to the point of land than indicated by the bow angle data and the calculations. So these factors must be considered when making a go, no-go decision, a stand-on or tacking decision. Well, sailors, I hope you learned something useful from this discussion. In this age of super electronics, it's easy to slip into button pushing only and to forget all about the basics. And this habit can lead to trouble when you least expect it. It also can weaken your basic skill set and reduce your enjoyment of the wonderful world of sailing and self-reliance. So study the basics and blend them into your navigation program and your regular navigation practice. Someday, you'll be glad you did. And happy sailing!